All right, we're going to talk a little bit about light. In fact, today and the rest of this semester, we're going to get a bit more abstract. Today, I would say, we'll try to take the between into it. Um, I don't know, it's hard to imagine. When I did this course, I thought this like, you guys don't think so? The idea that light is an omnipresent, that everything, every information we know about anything revolves around light, it means that light. We're going to talk about light in a bigger picture. In order to do that, we need to understand light as a smaller as its core, we need to understand that light is a wave. And that's what today is. I just chose this picture because it's pretty, first and foremost. It's a nice subject, I think. But it does touch upon something that I want to talk about. And I want to ask you guys, what do you notice about this picture? Just say anything about this picture. Say the most obvious thing. It's a picture of a. All right. So now tell me a few other things about it. There are many light bulbs. No, that's it's in the right direction. There are many light bulbs. What do you notice about this light bulb compared to the other light bulbs? It's not blurry. All right. So this one's um, in this picture. There just this light bulb. What is the source of light? Tungsten, it's this thing, whatever this thing is. Probably tungsten is one of those old school kind of tungsten burning lamps. You can see that based on this little pattern here. Is that the only source of light within here? Because there is light around here, right? Is that? Yeah, there's some reflection over here. From this light, or on maybe from the other lights, reflected on the glass. And if we were to look at, for example, this one, you would also see light. You see clearly that there's a light source here, right? And there is some light sources there, or maybe not the source of light, but there is light coming from those areas. What do you think those areas are? Try to draw the parallel between this and this. What do you think the light here is? It's the reflections, exactly. And what you notice about them is that they have this special shape, and that's an hexagonal shape. Why is it a hexagonal shape? Yep. Yeah, exactly. So it's a six-sided shape because the aperture, like the thing that closes and opens in a camera, is six-sided. Remember, you guys drew it for me, and that one time you guys were talking about cameras. So that if there are six of them, it'll make a six-sided um, diffraction, right? So that the property that's causing light to do this shape is diffraction. Sorry, that's kind of abstract. Let's move on a little bit. Here, what do you guys see? What is this a picture of? If you guys had to interpret this. Rain? Who said that? Oh, bridge. Okay, how do you see the bridge? Show me or explain to me. The bridge, so something is moving along this way? Okay. What do the lights represent? The lights on the bridge. These ones here? They're like these street lights? Yeah, because they're high at the level of this. I can totally see that. Realistically, I think this is just a Photoshop creation. Okay, but I could totally see that this could be like the perception of the street going off into a distance, whether it's a bridge or a street, it doesn't matter. With cars maybe driving along the sides, or maybe these are street lights or store front lights, and there's like street lights that are up at a higher level. They're making these lights are not all this shape. They all appear to be round, not because it's out of focus, but because of this idea of diffraction. Right? And okay, move on. So here's a really important thing. Who knows who Michael Bay is? Michael Bay, what does he do? Explosions. And what kind of movies does he do? He does the Transformers movies. If you notice, Michael Bay has a tendency of using one cinematography uh, technique way too much, and that is you guys know, the YouTube maybe? Lens flaring? Lens flares? So lens flares is when you get like this halo effect around a source of light. So a lot of Michael Bay's movies, for example, Transformers, will have like this camera sitting around in epic moments, and then the light kind of like this sunlight does this lens flare thing. I think J.J. Abrams is also really famous for doing that. Let me show you an example so you know what I'm talking about. If it autocorrects, that means you know he's got too many lens flares.
Isn't it annoying? Every movie nowadays has these over-the-top lens flares. I mean, look.
They're everywhere. The further we get... Yeah, we do.
Yeah, it's so unrealistic, eh?
So that effect is considered to be.
Oh my god. Turn off the lights. Follow me.
So you know what I'm talking about now? It appears in a lot of movies. Just some directors use it a lot.
Huh? We need to neutralize the lens flares.
You guys want to watch it? I have no idea what it is.
How do we do that?
Yeah, watch it. I'm curious to know what it is.
Mayonnaise. What? Didn't you pay attention in physics class? Ted, I've been bitten.
Bitten by what?
By a lens flare.
Am I the only one who thinks this is all insane?
You gotta kill me before I become one of them.
Well, I'm not gonna put mayonnaise on you.
Quickly, I'm changing. Screw it.
The lens flare comes about because light has a property that it can be diffracted, and that's quite interesting because you use that property of light to create a dramatic effect, and it ends up looking like this. So if you look at the sun with the camera or glasses in front of it, has anyone ever maybe looked at on a foggy day? If you look at halo around the source of light, that's all because of diffraction. We're gonna talk about that today. And it's also the way that light was discovered to be a wave, was because of diffraction. I was looking up as like, I'm looking for really cool pictures of light, and I came across this. I couldn't fit it thematically into today's class, but I decided I would just talk about it anyways because the first day back from the break, and we need cool things on the first day back from the break. This here is a sky that was overexposed. And I'll talk a little bit about overexposure, but I just also want to talk about something called light pollution. Light pollution is when there are too many lights from the city, for example, to be able to create a contrast big enough for you to be able to see the stars in the sky. So, for example, if you look up at the sky tonight, and it's a clear day, no clouds I'm talking about, and you look up, you might see like 10 stars. And if you look longer, you might see more because your eyes get adapted to the darkness. But you don't see this many, that's for sure. Right? And no one has ever looked up at the sky in Montreal or wow, to go up to your country house and you do look up, you can see more stars. Of course, the longer you look, the more you see, and that's because your eyes are getting adapted to the dark. This was a camera that's exposed the sky for a little bit longer, and so it took in all the light, and I made a picture of it. You can kind of see this. You guys know what this is here? This white part. Cool. I'll give you a hint. It's cool. At least it is to me. I don't know. So when you look at the sky, there is some stuff in the space, right? Most of these are stars, exactly. So are these, in fact. But there's also more to it. What does our galaxy look like? You guys know what the typical Milky Way picture looks like? It's a spiral, right? And then there's like a central bright point in that spiral, and you can imagine that you have a bright ball in the middle, and there's like a concentration of brightness in this shape like this. And now imagine this started to spin like that. What would it look like? If this was starting to spin, look like that. It's a spiral, and these are flexible arms, okay? So you would end up with a picture that looks like this. Right now, down, yeah, it kind of looks like this. I mean, it's imaginary. But galaxy ends up looking like this. But if you were to be somewhere along galaxy, in this galaxy, assuming that they're there, or you're looking in this direction, you'll be able to see one of these arms of the spiral. And that's exactly what this is. This is the arm of the spiral of our galaxy. You can literally see the Milky Way if you just looked up at the night sky. And that's pretty cool. And there's something I want to talk about here. But before that, I want to show you just a video because it's really trippy, and I think it adds to the mystery of light a little bit. So let me preface this by saying that we're not stationary. This planet moves pretty damn fast, if you ask me. And the universe also moves, but according to us, the universe is stationary because we move a lot faster than, or rather, we move a lot more in space than something. Talking about this. Here's the whole sky around us, right? So we are right here, right? And in a certain amount of time, the planet will have done this. That's what the planet does. So we went from seeing, let's say, this part of the sky to seeing maybe that part. And so what we see up in the sky changes. And that's in a day, a whole day. The planet does a full turn. So within a few hours, you will have seen quite a bit of the sky. So this is actually a time lapse of the planet looking up at the stars, and the planet moving looks like the stars. You can see the pause it right here. I want to point your attention to, and this does relate to the course, is how many times how many stars we see here. These are all stars similar to ours. Are they closer or further to us than our own star? Much further, much further. You guys know how close the closest non-star is? Like our sun is our closest star, yes. But after that one, which is the closest star, how far it is? It's many light years away. A light year is how far light travels in one or 1 year. Hold on, let's do some math here. That's how much light travels, how many meters in 1 second, right? If I were to multiply this by 6, that's how fast that's how far light travels in 1 minute. If I were to multiply this by 60, that's how far light travels in 1 hour. Multiply this by 24 in 1 day. Multiply this by 365. That's how far light travels in 1 year. So that's what 1 light year means, right? So that would be a light second, a light minute, a light hour, a light day, and a light year. Okay? The closest star to us is 4.3 light years away. Closest one. So take that number, multiply by 4.3, and that's how many meters away the closest star. That's not the point though. These stars are all really far from each other, just like they are really far from us. We could resolve. Our eyes are able to determine that this dot and this dot are different, right? Everyone can see 2 dots here. However, if I were to look at just that dot, well, actually, is it just 1 dot? Is it 2 dots? Or is it a clump of dots? We don't actually know, right? And that has to deal with some concept of resolution, which our eyes and our optical instruments are able to do, which we're going to talk about maybe by the end of today, if not tomorrow for sure. And so we look at this and we're saying, oh, wow, there's so many stars. And what is the first question that anyone asks when they see this is, what is the likelihood that life exists out there? You guys have an answer to that? What is the likelihood? Give me a qualitative answer. Likely or unlikely? Pretty likely. You guys know what proteins are by now, I guess? Okay, good. Proteins are made up of what kind of molecules? Amino acids. And they're what kind of bonds connect each amino acid? You guys are all in health, right? No? You're not. But the rest of you are. What kind of bonds connect amino acids to each other? Covalent, yeah, but there's a special name to it. They're called peptide bonds. They're called peptide bonds. Does that ring a bell? Peptide bonds? Yeah. Okay. So peptide bonds are what connect amino acids, and as you know, a protein is a string of amino acids. So a protein that's made up of 10 amino acids. They're made up of one bond. So let's just take one. And this has each amino acid has something like 8 different possible folding parameters. So this amino acid is folded in 8 different configurations. So this one has so in total, for a 10 amino peptide bond, you have 8 to the power of 10 different possible ways of folding. That's huge. We are going to calculate. It's going to be a big number. 1073741. You're asking one person. A billion different combinations, or just 10 amino acid peptide bond. And if I were to just add this, it would be way more involved. Now the idea that life exists because of protein is actually quite well established. The first thing that came to And for this RNA molecule to have spontaneously come together by smashing a bunch of atoms together is very, very, very unlikely. Right? So if you took like a bunch of carbon atoms, a bunch of hydrogen atoms, a bunch of oxygen atoms, throw in some nitrogen, maybe, and you just kind of like randomly put them together, what's the likelihood, in your opinion, what's the likelihood that you'll spontaneously perform a protein? High or low? Very low. In fact, so low that we would consider it to be impossible, right? Let's say that number is a billion, right? It's way more than that. Let's say that number is a billion. Whatever that number is, there are way more stars than that probability. So if on every planet there was a whole bunch of atoms being smashed together to form RNA or proteins or whatever, it doesn't matter because there is so many more stars than that probability. So let's say, Leo, I said, okay, think of a star in the sky, and Adele, think of a star in the sky. What are the chances you guys would think of the same star? Very unlikely. That's still more likely than, or sorry, smashing together atoms together would be more likely than you two guessing the same star, right? That's how many stars are. So the answer to, is there a chance of life being somewhere else? Absolutely, it wouldn't make sense. Winning the lottery, likely or unlikely? Unlikely. The 649, the amount of combinations possible is 49 factorial divided by 44 factorial, which is something like 10 million. Okay? That probability is very low, but if you played the lottery a billion times, are your chances good or not good? Very good. It's the same thing with here. So the likelihood of creating life is not very likely, but there are so many opportunities that it does become incredibly likely. Okay? Huge. The universe is huge. So now we're looking at this and we're seeing all these different stars and we're resolving them. We can see a bunch of them. We can't even tell you that that's all there is because we're not able to resolve that well. Now let's get into why I'm talking about it. What you can see here is that you see less stars here because you're close to stars that are above the area. But you can't see them when you're looking far away and you're not looking over the city line. Now I want to show you a little picture. So if I were to now take all those frames that we took and compile them into one picture, what we would see is for example, when you started videoing, that star was there. When you finished videoing, that star was there, right? And so you know how much time elapsed between that star being in that position in the sky and that star being in that position in the sky, right? And based on the amount of degrees that it did, and also in relation with the other stars that you see, you can actually determine how far that star is, right? Because you have an angle of vision, right? So this is your initial angle, this is your final angle, right? And this is the angle that you would have seen with your eyes between there and there, would be creating this idea, this triangle, basically, of how far that star went in a certain amount of time. So we're using light again to identify information about it. And this idea comes about quite often. All right, that's the introduction. We're talking about lights as a wavelength. Okay, and we're gonna. All right. So, is it pronounced GIF or GIF? GIF? Who says GIF? All right. I'll see you guys after class. You fit. It's pronounced GIF because I said so. No, I'm kidding. There is no real thing, right? So some people say GIF, some people say GIF. The people who created it call it GIF, but in the English language, these sequence of letters would produce a hard G like Gabriel or something like that. A soft G like George. So that's what it's supposed to be through the English language. Through the creators, it's GIF. GIF. I'm getting confused. The point is that they both exist. They're both possible. All right, and then that's the same idea that perplexed scientists for a long time about light. Is it light? Is it a particle or is it a wave? Newton, he was the old school guy who's like, he's like your grandpa, and he sees things in a very systematic way. He's a particle believer. He thinks that everything is a particle, that forces can act on it, that it has a mass, and that it obeys the laws of Newtonian physics. So that's the old school kind of way of thinking. And then Huygens came along and he said, no, 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 it's definitely a wave. I came up with this experiment. It proves that it's a wave. It cannot be a particle at all. He's like the new school kind of guy who's the one who you always see uses the latest technology, you know. He's like, he's got the Apple Watch connected to his ears or something, or something like that. I don't know. But he's doing all the cool, all the new stuff. And then there's Einstein that comes along. He takes both of them and says, well, no, they're both cool. So he's got the tungsten lights in his apartment, but he's also using an Apple laptop to write screenplays on his cafe time or whatever. He's the hipster. No one likes him. Everyone is a hipster to a certain way. There's just no one admits. So now there is this idea that light is a wave. And if you go back to the early 19th century, the early 20th century, this idea is quite weird. The fact that light can be a wave. This is what Huygens proposed for waves, not light waves, just waves in general. And he said that things that are like waves behave like waves. That wavefront is going to be made up of many particles. How many particles are in a line? An infinite number of particles or infinite number of points create a line, right? Let's just take three for example. And you'll see that each one is creating a wave. So this wave here is the wave of this particle. This wave is part of that, part of this, and this one is part of this. And in between them, there's a whole bunch of other ones that I haven't drawn, that each are going to have their own waves. And then what is it going to create here? Another wavefront, right? Another wave, right? That would be the next wave, and that's how that is being described. And if you had a circular wave, right? So you have a circular line, then you would have particles along each of which are going to make different their own wavefronts, right? And when you put all those wavefronts together, you get another circular wavefront, okay? Just a bit bigger. Now, imagine that you have this wave that's coming up against this opening here, right? Okay? You have a wavefront that's coming up against this opening here. Now, this black stuff here is a barrier, and it doesn't allow the waves to go through. But the opening does allow waves to go through. And so you have to imagine that each of the waves that are making it to this opening, and it's only about this wide, is going to be made up of many, many particles, right? And there's a particle here that's going to have a wave that's going in maybe that direction. This one's going in that direction. But look at the ones on the side. This one is going to produce a wave like this, right? And so the wave that's being produced like this, and you can see that there's clearly a wavefront going in this direction, going in this direction, going in this direction, going in this direction, and a wave here might only be going in that direction, and so on and so forth, right? So I end up with waves going in every single direction. A wave that was only coming upwards hits an opening and goes in all the different directions. That makes sense? Right? That's for all waves. So if light is a wave, it should also behave like this, right? And so that's what the experiment was. So you have this hypothesis that if light is a particle, we should be able to see a pattern like this. Light goes through a slit, and only the parts that don't hit a wave are going to, that don't hit a barrier are going to hit the screen. you would get a very sharp circular image like that. In fact, what you end up noticing is something that looks like this, called a diffraction pattern, right? So this is not what happened, and this is what happened. Okay, we have to explain that now. Huygens took this and he said, look, data is right here, light is a wave, particle can't be true. What else do you want me to say, kind of thing? So this guy named Young came in and he actually proved this with an experiment. Any questions on this? It's about to get quite complicated. So here you can't really see it super well. You can see the six-sided star here, which has to do with the aperture. But what I want you to notice are these diffraction patterns that look like that. You guys see it? Those little halos around the lights? Those are light being diffracted because of the camera aperture. And we're going to try and explain that with Young's double slit experiment. So what Young did was he had a very small opening with a dot here, and he allowed light to come through, right? So what happened is light, instead of light going straight down, I'm just trying to write on the wall. Instead of light coming straight down, first of all, it opened up like this. That's fine because light goes in all directions. So far there's no fantastic discovery. You close one of the slits and you let shine through, and this is what you see on the wall. This rectangle here is, if you were to look at that wall from that perspective, you can see that it's just bright here and darkness on either side. If you did the other split and close this one, then you would get the same thing. And when you had both of them, his theory was you should be able to see this if it's a wave theory. You should be able to see this if it's particle theory. And what they actually ended up seeing is the wave theory pattern. All right, and this is called a diffraction pattern. We're going to refer to that a lot. Okay? Pattern. I kind of jumbled my end there. The diffraction pattern. All right, I'm going to use that term a lot. So be familiar with it. Any questions on that? So we need to recall this concept of path length difference. And remember, we had those speaker experiments where I had two speakers and you guys moved your head a little bit and you were able to get the minimums and maximums. You guys remember that? So I want to remind you of that. Here I have a wave going from speaker one, but this is actually just split one. From speaker one, the wave ends up on a positive end of the of its phase, right? It's on the, let's say, top part of its phase. And then here, the same wave travels the same amount of distance, same wavelength, same distance. Are they going to be in phase or out of phase? Yeah, they're absolutely going to be in phase because there's no distance that separates them. They're both traveling at the same speed. They both travel the same distance. They both have the same wavelength. Therefore, they have to be in phase, right? Same thing here. You can see that this one is ending on a crest again. This wave is also ending on a crest. So therefore, there's supposed to be constructive interference. They don't necessarily have to have the same number of waves traveled until then, right? So this one might have been 10 waves, this one might have been 11 waves because it's further. But they both ended up on a crest. So they both interfered. Here, you can see that the waves went and it ended up on a trough, whereas this wave here ended up on a crest. So if one ends on a trough and the other one ends on a crest, then that means they have to interfere destructively, right? And so here you're going to hear the speaker, hear anything, right? And you just have to make sure that this one is out of phase with this one. What does it require to be out of phase? Totally out of phase. You guys remember this? Has to do with wavelength. Yeah, absolutely. You have to be half a wavelength out of phase in order for it to deconstruct, and you need it to be full wavelength in phase for it to construct. Right? And we're going to build on that. That theory is very strong part of understanding the double slit experiment. All right. So I wrote that here just in case you guys might have forgotten it. So now we move on to this double slit. Right? We're going to be doing some drawing to make sure you have some space. All right. So here's my double slit. All right. And I'm shining some light through this, right? And I need to know a few pieces of information. One, that there's a separation between my slits. I'm going to call that separation D. I also need to know my distance between my slits and my screen. I'm going to call that distance L. And finally, the wave that's coming in this direction has to have a wavelength lambda. Okay? That's the information I need. What I note on the screen is that I'm going to get a pattern in which kind of looks like this. Without the spike is just a glitch in my pen here. And so you have an area of really bright spot in the middle. Really bright spot in the middle. Kind of a two dark spots. Then it gets bright again. So what this is going to look like is 3 bands. There is more. I just decided not to draw that. So there's three bands that I can see on this side of my screen. Yeah. There is a light ray that's going in this direction towards this bright spot, right? And there's a light ray coming from the bottom slit, also going to that bright spot. If they were to produce a light spot, are they interfering constructively or destructively? Constructively, exactly. That means that if this were a wave, at the last second I get a spike. Okay, I'm too stubborn, I'm going to redo it. All right. At the end of the wave, I'm gonna decide to draw it as a crest. It doesn't matter if you drew a crest or a trough. But the point is that whatever it is, my next wave has to have that same characteristic. Like that. Also ends up on a crest. So here I get constructive interference. If I were to draw a normal line, I would be able to measure this angle and this angle. And seemingly from my diagram, these two angles, are they the same or different? They're the same. Do they look the same? No, they're not. They're actually the same. Actually, they might look different, but in reality, they're the same. And the reason for that is because L is way greater than D. Okay? If L is way greater than D, then and they meet at a very far distance. So these two rays, I'm going to call this ray 1 and ray 2, just for explanation's sake. If ray 1 and ray 2 meet at a distance very far away, what can you say about ray 1 and ray 2? Yeah, absolutely. When two rays meet at or two lines meet at a very far distance, then those two lines are considered to be parallel, right? So if it was very close, you can see that these two angles are totally not, right? This angle is way smaller. However, if it was really far, then this angle becomes closer to this one. It kind of looks the same. And if we're talking about practically infinity, right, not reality, practically infinity, these two angles will be the same. Therefore, they are parallel. So you can say that angle 1 and angle 2 are equal. for all intents and purposes. You can say that theta 1 is approximately equal to theta 2. Now, let's draw a line that intersects from one slit, intersects the other ray perpendicularly. So here I have a right angle here. Everything beyond that intersection. If I were to say anything starting from here all the way to there, and starting from here all the way to there, they're exactly the same distance, right? And if they behave similar, if they're the same wave, same phase, then you'll get constructive interference. That means that this distance here is the path length difference. Okay? Now, let's define that. So I'm going to call that path length difference delta D, right? But let's not hold on to that value delta D for a second. So I'm just calling it that temporarily. This angle here must be equal to what? This angle that I drew right there. If I were to follow this geometrically, what would this angle be? 90 degrees? Well, I know what you're trying to say, but that's not the answer I'm looking for. Imagine I have my book like this. Yeah, 90 degrees, right? If I were to angle this part of my book so that it aligns with this line here, right? Okay, I mean, I drew it wrong. But that angle would be equal to this angle here, right? Because I shifted everything. And so this is still at 90 degrees with this line here. So if this was theta, then this angle is theta, also theta. Again, my drawing is not very good, but it is. All right. So we know that that's an angle theta. And we have a right angle triangle, which is fantastic. Because right angle triangles are easy to do math with. That path length difference that I called the delta D very temporarily is going to be the same as saying that it's D sine theta. Because I have the hypotenuse of that right angle triangle, which is D. I have the angle, which is theta, so I can find the length of any of the other sides of the triangle. And if that path length difference is a multiple of the wavelength, do I get constructive or destructive interference? Constructive. So if I were to say D sine theta is equal to some multiple m of the wavelength, and m is going to be an element of integers, then I have constructive interference. If I have a half multiple of the wavelength, then I'm going to have destructive interference. So it's all about that path length difference. If the path length difference is a multiple of the wavelength, constructive interference. If not, destructive interference. Everyone's following so far, hopefully. I want to just add something for you guys. It's going to make solving the rest of the problems for today a little bit easier. Assuming that I had a ray going like this, an array going like this. Okay. If I were to talk about this geometrically, I can say that this angle here is this angle divided by 2, or 2 times this angle rather. The reason for that is because these lines, these dotted lines that I drew, all of them, are parallel. If these 3 lines here, these 3 dotted lines are parallel, and this is far enough that this and this are parallel, right? That means that this opening is exactly twice as big as this opening. Okay? That's going to help us solve some problems later on. It might not deal with what I just explained here yet, but you'll need it. Okay? I'm going to give you guys the first problem. I want you guys to work on it. And the way I want you guys to work on it is very simple, right? Because it's not an easy topic. First of all, identify the variable. Tell me what D is, what L is, what lambda is, what the angle is, whatever it is that I'm giving you, identify it. Second thing you're going to do is draw a diagram. Okay? Once you've done those two, the rest of it is quite easy. Okay? So try to doing that. My throat's super dry. I'm going to get a glass of water. I'll be right back. Here, you guys don't really know what to do with. What is that Y that I wrote down there? What does it actually represent? the height of the point where they meet. So if I were to go back, where would you draw that line? Here? Okay, that's the distance between there and what? The center? Okay, so let's go back to the question. It says the distance between the two slits is second order bright fringe. Yeah, absolutely. So exactly what Leo said, right? This would be the second order bright fringe, right? Because the first one is right there, and the second one would be there. The distance between that and that is going to be what we call y. Now you can use that. Maybe that helps you a little bit to solve this problem. Keep on. Don't be afraid to check it out. Please. Do me a cool. Yeah, interesting. Do any of the teachers use this? Huh? Works quite well. I added in something here in blue that might help you a little bit. could you tell me about these three angles? They're all the same, right? They don't look the same, but practically speaking, they are the same because this distance is 0.03 millimeters compared to this, which is 1.2 meters. So it's like a 10,000-fold difference between this and this. So you can practically say, yeah, that's going to be pretty far. Right? It's not technically parallel, very close. What I would start to do based on this is you know that this blue triangle is going to help you solve the angle for these other ones, which is what you need, right? So how do I get this angle? Well, I have the length of this, right? Given to me as 1.2 meters, and I have the height of this, which is given to me at 4.5 centimeters. So if I use tan or inverse tan, I can easily find that angle and apply it for the other two. So I would start there. Don't forget to convert your units, because that's super important. So remember an angle for me? Yes, small angle. 2.15, sounds about right. 2.15 is that angle. Now I also know that I have this equation to deal with, so d sine theta equal to m lambda. They give you the m in the question, it's 2. They give you the d, you found the theta. So you can plug everything in now. So this is going to be 3.00 times 10 to the minus 7 meters multiplied by the sine of 3.15 is equal to 2 times lambda. And then lambda is going to be equal to, what did you guys get for lambda? Still no one? What'd you get? Now, it should be in meters. If you kept everything in meters, it should be in meters. If you get a number here that's like 20 meters, is that realistic? You're looking for something probably in the visible spectrum. The visible spectrum is between 400 and 700 nanometers. 400 representing red or blue? Blue, and 700 representing red. So what did you guys get for this one? Yeah, so that would be 560 nanometers. You know what color that is? roughly speaking. If we can see between 400 and 700, and 550 is pretty much in the middle, that would probably be like green. Okay, guys, take a break. Come back in 7 minutes, 8 minutes. Yeah. Okay, so this, we have to remove questions. So set the sixth one on right. Right, so that's the right one. A is 4.72 central maximum. So this is the central maximum.
But there is coming from there and not in the middle of the.
Yeah, you're right. I'm not saying it is. I'm just saying if I have this and I have that one, I can find this angle, and because they're all parallel, using this angle to keep it the back, right? And then I can use this equation. Right? So this blue triangle is not has nothing to do with light at all. Right? It's just geometry. No, I didn't respond to your email. 10 on Wednesday. Does that work? Okay. Okay, let's start. We have something called we just did the double slit experiment. Double slit situation. There is a special situation as well called the single slit experiment. And the single slit experiment is, I would say, the more complicated of the two, just because it's harder to visualize what's happening really. All right, I will go through that. But it might not be clear when you start studying in the context of all the other ones. So one would think, how could you get a diffraction pattern if there is only one slit, right? If it's just one slit, all the light's going through, there aren't waves that are interfering constructively or destructively. How could it be that you have a diffraction? Particularly if you do have diffraction. If you remember just that diagram that I had earlier on in the slide, right? You had a single slit and you still ended up with a fuzzy kind of circular shadow thing. And that's a diffraction pattern. And so how does it behave? How do the waves behave in order for us to get a diffraction pattern out of a single slit? And the truth behind it is that you can't really consider an open slit to be just one slit. You have to consider an open slit as many open splits. So let's take some examples on that. And we have to refer to Huygens principle here, all right? Because when the wave there's a wave coming in, eventually the wave's going to get closer to this opening. Okay? There's going to be a point there and a point there that are going to each produce a wave, right? And every other point in between, of course, are also producing waves. Therefore, they are basically acting like waves coming in together, and it might interfere destructively or constructively. But the math is a bit more complicated, especially for the constructive interference. So complicated, in fact, that we're not even going to do it because I don't have the math myself to be able to even teach it to you guys. but we do have the math available to teach the dark spots. So what I'm going to assume here is I have a diffraction pattern that kind of looks like this. And we're going to consider the lines that all come together to form destructive interference. Another thing that I need to consider is the distance between this ray and this ray. And if my whole opening here is, in this diagram, we call it A, so I'm just going to stick with that for simplicity's sake. So this whole opening is A, like that distance is A. And we're considering the ray that's at the very top and the ray that's at the very center. So what would you say the separation is between these two rays? Absolutely. A divided by 2 is the separation between these two sets. So let's make that drawing. Where this distance is A. Something like that. We can use the same kind of reasoning that we used in a double slit experiment. We can say that, well, if they're interfering destructively, so what must be the phase difference between these two rays? Half a wavelength, right? So let's figure out what the path length difference is. So let's draw a right angle here, and I have this line which is going to be A over 2. That's my hypotenuse. A over 2 with my angle, and my path length difference is going to be A over 2 sine theta. A over 2 sine theta is going to give me my path length difference. And we're saying, I'm telling you now, that these two rays are destructively interfering. That's right terminology. Destructively interfering. So this has to be equal to some half multiple of the wavelength. Since it's the first one, all right, lambda over 2. That is, in fact, m lambda over 2, right? And that's strange. Look at that. My 2's cancel each other out. And so I end up getting that d sine theta is equal to m lambda for destructive interference. Sorry, I meant A, not D. A sine theta. To me, that's strange, and hopefully to you it's strange too, because look, for the double slit experiment, d sine theta must equal to m lambda is for constructive interference, whereas in a single slit experiment, it's for destructive interference. Same exact equation, but for a single slit, it's a bit different. And I don't want you to write this, right? Because it's going to be wrong, obviously. But we cannot use this logic in order to find the constructive interference. Let's do the same exact procedure, except if I wanted it to be for constructive interference, it wouldn't be divided by 2, it would just be m lambda. So what I would get is that the path length difference is equal to A over 2 sine theta is equal to m lambda. And if I just move my 2 over, I'm going to get A sine theta is equal to 2m lambda for constructive interference. Where's the paradox? What doesn't work? Look at this equation and look at this equation and tell me why that's impossible. It's the same equation. Name me an integer for n. There's 1, and then there is 2. So if I put 2 there and 1 here, I can't have constructive and destructive interference happening at the same time, right? So this wouldn't work for 3, but it would work for 4, right? So 4 here would be the same as 2 there, and I'll get the same value again. Can't have constructive and destructive interference at the same time. This equation doesn't work. The math here doesn't hold for constructive interference. Therefore, we can't use that logic. For your level, what I want you to do is, if I were to ask you where is there constructive interference, you would find 2 adjacent destructive interference points, and the midpoint between that is going to be the constructive interference. Okay? So there's going to be a destructive point there, for example. I'll draw this in another color. Right, so I do this whole calculation, same exact thing. I would do it for an adjacent dark spot, or for a destructive interference point. And I have this destructive interference point, and midway between those two would be my construct. Yeah. Or you're talking about m plus or minus half of times lambda? Yes, you're right, but I'm only talking about the first one, right? This equation applies to the first one. So it would be 1 minus a half, which would be a half. All right, makes sense? So use that, try to solve this next problem. It's very similar to the one we did before. Sorry, my throat's super dry. I'll be back. So I added a drawing to maybe help you visualize a little bit. Oh, it's a dark fringe, eh? My arrows are pointing in the wrong area. All right, so again, we can always start with making a right angle triangle and trying to find the angle. So I'm going to do that first. I have this triangle here. I can say that inverse tan is going to be equal to 2.00 times 10 to the minus 3 meters over 0.5 meters. That's going to be my angle. What angle did you guys get? Should be very, very, very small. Yeah. That's my angle separation there. And that's going to be the same angle as this. The same angle, I mean, yeah, of course it's the same angle as this, because this screen is so far away, you can consider their angles to be the same. And therefore, I can say that A sine theta is equal to m lambda. In this case, is this an m of 1 or of what? Yeah, it would be an m of 1 because it's the first dark spot, right? Well, it can't be 0 because in this equation, the A sine theta is equal to 0 lambda. That doesn't give us any. So it has to be 1 for this one, not 1.5 because it's a dark spot, 1, right? And not A over 2 because we've already accounted, we've already removed the 2 out of the equation. So it's just A at this point, okay? So it's going to be 0.450 times 10 to the negative 3 meters times sine of 0.07 degrees is equal to m, which is 1, times lambda. Or is it just basically just equal to lambda? And if you did the math right, you got a lambda of in Cincinnati. Closer to red than it is to blue. You can say orange, something like that. Ah, forget it. Keep getting it. Okay, this is an orange maybe. Maybe closer to yellow because it's still close to green, kind of. Any questions? If not, let's move on to the last situation. And that is a situation where you have many, many, many slits. All right, so many that you can't even count, for example. All right, and you have this kind of diffraction apparatus. What's going to produce is what we call this thing is a diffraction grating. And whenever I say the term grating, you can basically assume that I'm talking about something that has many, many slits. And if before we even talk about that, and we try to do the math, we've observed experimentally that this is the kind of situation that you get. If you had a single slit, right, you'd have a really thick band, and then two narrower bands, and so on and so forth. And when you have two slits, you have these narrower bands, so you have more bands with a specific area. And here you have three slits. As you can see, what's happening is that the bands here are getting narrower and narrower, and they're getting further and further apart. Okay? So these two bands are going to be further and further apart than these two bands. And as you add more and more, that's going to be, yeah. 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 506. 56 would be to the power of negative 8. Yeah. All right. All right. So you have to notice that these fraction patterns are going to look like this. Now, if you have many, for example, a diffraction grading situation, what's going to happen is that these peaks are going to be higher up and they're going to be further distanced away from each other. It doesn't matter though, because you could basically assume that this goes on forever upwards and this goes on forever downwards. And what we care about is locally what's happening on this side. Now, the simplicity of this is beautiful because what's going to happen is that you're going to assume that this is exactly like a double slit. And you're only going to consider a small section of your grading where there is only two slits so that you can apply the double slit pattern. So you can say that you have d sine theta is equal to m lambda for constructive interference, and you're going to have d sine theta is equal to m minus half lambda for destructive. Okay? So very similar to double slit. One thing that I didn't ask you, and that I could totally ask you, and therefore will ask you, is I've given you this y value, but I could easily ask you, what is the thickness of each of these bands? If I were to ask you the thickness of this band, how would you do that? Absolutely, right? So if I were to tell you to find the thickness of this band, well, what I would do is I would find the angle at which I get destructive interference here, the angle at which I get destructive interference there, and a change in angle is going to give me the width of this kind of like non-right angle triangle. I'll let you figure it out. But if I can actually ask you to do that for me in any one of these bands, right? If I wanted the thickness of that band, right? If I wanted the thickness of this band, then I would just do this. I would do the destructive on either side, find the difference in the angle, and find the thickness inside, or this value, right? And that would be the thickness of my band. I have some assignments, not assignments, but problems for you guys to practice with. When you're practicing, just keep that in mind, all right? You can solve for the thickness of each of these bands. There is a more complicated mathematical equation to find out the brightness of these bands, so how high they peak. We're not going to go over that. That's more university level. So knowing that, and this, we'll do this problem and then we'll take off for today. I want you guys to solve this problem. I'm just going to add a letter C for you. All right, so while you're working on that, make sure you also answer C. And that's going to be, what is the relationship between the thickness of the band and the wavelength? always start the problems the same way. Look at the variables that are given you, make a diagram, work from there. Yeah. So maybe the question is more often, so how many lines, how many splits? Either there is one small mistake in that. one is perpendicular. I would divide that by 2. So pay attention to the question, right? It says that the distance between the dark fringes on either side of the center line is perpendicular. Not between the center and perpendicular, between the two directions. Right? So if you're going to find another trig, you need to divide that value by 2.
Between the grading system of the thing, the slits are.
No, okay, so you can assume that the slits are negligible in size. Slits are very, very minuscule.
Je vais genre un mètre divisé par 6.
Yeah.
Ah.
What did you guys get for the angle? Oops. What did you guys get for the angle? Degrees. All right, perfect. And so now we can use that to solve this equation here. What's m in this case? This is the angle to the first dark fringe, right? So is it 1? Or is it another number? Remember, it's a double slit experiment. So it should be not an integer. It should be a half integer. So in this case, I'm going to get d sine of 0.07 equal to 1/2 times lambda. Okay. So I can solve for my d here. What the heck is that? Is there, like, doesn't that the number one rule of lab? Is that you're not supposed to run in it? Oh. Oh, this is bio, I suppose? You guys are doing cardiovascular system? So what did you guys get for D? No one? Laura, what'd you get? -4? Perfect. So I have, this is my distance, this is my size per slit, right? Ugh. So if I were to solve this, my D, what it represents is how wide apart are each slit, right? And if I wanted to know how many slits there are in a meter, or yeah, how many slits there are per meter, I would just have to do the inverse of this, right? So 1 over D would give me my gradient. All right, so let's do that. 1 over D is going to be 1 over 1.93 times, it should give me something like 5,000. Like that. What did you get? $5,181 splits per meter. All right. And that's really on this side of things. I wanted to ask you guys this bonus question here. What is the relationship between the dark fringes and the wavelength, or the distance between the dark fringes, rather? Let's say the wave. I'm going to show you a video. I want you guys to have a hypothesis in your mind. Do you think that the slits are going to, the fringes are going to be further apart, or are they going to be closer together if the wavelength? I want you to think about that. Try to rationalize it. And then I'll show you just a simple demonstration.
Thomas Young.
So let's just watch this real quick and see what that relationship is. Volume.
Proved with thousands of slits in it, and I can prove that the following way. I've got myself a brand new, where is it? I've got myself a brand new purple laser pointer. Check this out. There it is right there. I'm going to turn off the lights and make this a little more interesting. So there it is, and I'm planning to show you how the light goes through here, and it is no longer just a single beam. It will be lots of beams. Oh, cool. So through those slits, and we'll see exactly what additional slits do, but through those slits, I'm getting a whole bunch of dots. And the angle of separation between them, look at this, I can move the laser pointer forward and back. Sorry, if I move the laser pointer forward and back, I should not, dang it, I should not be noticing any change, but I definitely am noticing a change, so that's kind of frustrating. So if I move the laser pointer forward and back, I should not notice a change. There we go. Now I'm moving it forward and back a lot, and I'm not noticing a change. Problem is, I'll show you what the problem was. As I'm going to different regions in this, I'm getting all kinds of weird bending, like the plastic is not uniform. Oh my gosh. Wow. Yeah, that is really weird. Oh, also, yeah, I'm going forward and back, and I'm at an angle. That's probably why it is. So if I try not to be at an angle, if I move forward and back, I get very little change in the separation. Now, that's with, wait a second, isn't wavelength related to frequency? Let's see if we can say the speed of light is frequency times wavelength. So wavelength must be the speed of light divided by the frequency, right? So that's a very high frequency. So it means it's a very short wavelength. What if we try something that's more like green? What are you expecting with green? I guess we'd get a little bit more more splitting? Yeah, a little bit more splitting with green. And we go like this, forward and back, and we don't get much of an effect. And that's really cool. Here's something else that's cool with this. I can get reflections, and I can get bending as it goes through. So I can even make this really neat circle. I think this is pretty cool. Do you think this is cool? I think it is. Well, whatever. Maybe you don't, maybe you do. Going through, not going through. Check that out. Yep. Single dot, lots of dots. Cool. Those are bright fringes, and right in between the bright fringes are the dark fringes. That's pretty neat. Now, what if I go to an even better diffraction grading? That's what this is called. Yeah, it's got so many. Look at that. Wow, that's amazing. That is incredible. Check it out. And you can get some reflection and some refraction. That's really beautiful. And I could go to red. Now, red's got a really, really low frequency, so a really, really big wavelength. And if I go to my equations, remember my equations say something about d times the sine of theta. Wow, you can't even see that, especially with the light off. D times the sine of theta is equal to m times lambda. That means the spacing has something to do with like the sine of theta, right? So the sine of theta is sort of like lambda divided by d. Ooh, interesting. And maybe we need an m up here, but we can kind of put it in parentheses and say, if I'm just looking for the spacing, then I guess the bigger the wavelength that I have, the bigger the spacing I'm going to get. And the closer the lines are, the bigger the spacing I'm going to get. So I'm going to get this guy here that's red. Big wavelength, right? And I'm going to get these here, this d is really, really small. Boom! Look at how much those are spaced. You can't even see them when I go up here. Wow, so I guess you get pretty bored if you can't see them. But look at that. These are bent so incredibly much here that you can only see 3 dots at the maximum. And I frankly can't get you any more of them unless... Can I, possibly? No, you can only see 3 because they're bent so much. Wow, cool. And then finally, I have this really amazing sheet of stuff that I found... Whoa! Here, I'll turn the light on for this. I found this stuff inside of a monitor. Look at what it does to the text as I lift it up from the text. What? Fascinating. And so you can ask yourself, what would this do if there were a green light shining through it? And here we are. It turns out that that green light is then spread into a line, and look at those 2 bright points. So this must be some sort of a diffraction grating. Sorry, my laser's kind of flaking out on me a little bit. There we go. We see it nice and dim now. There are those 2 bright points. But if we can get it to be all the way on again, there, now you see that nice line. And I can make this form a full circle like that, which I think is really pretty. And I'll let you try to figure out what it is and how it works. Reflection, diffraction. Yeah, beautiful. So we are entering some really interesting stuff, and we're just about to get to some great physics. So stay.
Right, so increasing the wavelength would mean increasing the spacing between each grading. There is one thing I saw once a long time ago that was really cool. Give me 2 minutes. If I can find it, I'll show it to you. Otherwise, we'll just call it a day. It was a laser diffraction animation laser. Let's try that. It was. I really want to find this. Give me a second. I can't find it. Okay, look for it tonight, and I'll show it to you guys tomorrow if I find it. Otherwise, this is pretty much where I wanted to stop today. Don't want to go into resolutions because I think it's different and it requires a different. So I wanted, this is a good natural part to the stop. I'll see you guys tomorrow in a few. Yeah. Okay. So if I have, I'm to the board. This is the dark thing, right? That's dark. That's the thing that this is good. So after central max is 4.50. This distance is after this distance. Okay? Because through the center, you create this triangle. This is, yeah, you would be, this would be, for single side, right? But I'm saying for this, why did you divide it by two? Oh, yes, it's divided by two because it's the first chart. So here, n is equal to 1. So you have the 1 minus 1 half. So this is going to be half. Then you get you try doing it in different steps. So do this first and find the theta. I think it's 0.0. I think it must be 0. Try punching it in your calculator.